Well, hello everybody. Welcome to another day of algebraic structures. So if we remember what we did last time was we were working on some homework for generators and cosets, and so that's what we worked on last week. And we're actually going to spend some time talking about both of those in a new context, combining together to come up with some nice results about groups. And there is class today. I'm sorry. I enjoyed the April Fool's joke though. All right. So what I want to say here is if we're working with subgroups, we say that H is a subgroup of a finite group G, or in general of any group. What we're going to say is that the order of H is a divisor of the order of G, or the cardinality of H is a divisor of the cardinality of G. This would still work with infinite groups. We just would have to work with a different definition with divisors and stuff. And so generally we'll focus on finite groups in this case. But the point here is that if I find the cardinality of any subgroup of a group, then the cardinality of the subgroup will divide the cardinality of the group, or that is the order of the subgroup divides the order of the group. And this divisor, this is Lagrange's theorem, and the divisor is going to be, we're going to call that the index. So the index of H and G, or the index for G of H, is going to be equal to K if the cardinality of G is equal to the cardinality of H times K. Now notice that this is a theorem, so this is something we have to prove, and so what I wanted to do is think about this within the context of what we've been doing, so I'm going to go up to the board here. All right, now I do want to point out this is a pretty amazing theorem because it says that if we know the cardinality of the group, then any subgroup has to be a divisor of the cardinality of the group. So we can only have subgroups of certain sizes. We can't just have arbitrary subgroups. And so this really limits the number of subgroups we can have. It limits what we can check for. And so it is a very helpful theorem. But to get to the proof of the theorem is what's going to happen is, let's suppose I have a group G and H is a subgroup. If we recall last time, what we talked about were the cosets of H and G. And in particular, we looked at right cosets, but we could also look at left cosets. But what we determined was that a couple of things is that if I find any right coset of H, then the cardinality of the right coset is the same as the cardinality of H. Also, if I take HA intersect HB for any A and B and J, either this is the empty set, or HA intersect, or HA is equal to HB. And what we proved this explicitly, but we also showed that being in the same, or having the same right coset is an equivalence relation. So therefore, being in the same right coset is an equivalence relation, so the right cosets therefore form a partition. So therefore the intersection between any two distinct one is empty. And so either your intersection is empty or they're the same right cosets. Now using this, what I can do is talk about, well, if I want to find the cardinality of G, since these cosets are going to form a partition, because this was an equivalence class, we also had that the union of all of these was just all of G. So if I take G as just the union of all A and G of my right cosets HA. So remember my right, I have H. I multiply by some element. If it's in H, I end up back in H. If I'm some other element, I might end up with some other right coset. But basically, because I can multiply by any element in G, I'm going to get all the elements of G if I take the union of all of the right cosets. Now, if I want to find the cardinality of the union, what I should do is add up the cardinalities individually and then subtract off the cardinalities of the intersections 2 at a time and then add them 3 at a time. And so you could talk about your addition principle. But since these are mutually exclusive or disjoint sets, if I want to find the cardinality, what I get is that this is equal to the sum of all A and G of the right cosets. So if I add up all of the cardinalities of the right cosets, because they're disjoint, there's no intersection, I don't have to worry about subtracting off. I add up each of these cardinalities, I get the cardinality of the union, so I get the cardinality of G, which is the union. But what we just claimed is that each of these has the same cardinality as H. So if I count the number of distinct right cosets, and let's say that there are n distinct right cosets, what I'm going to end up with is n times the number of cosets I have times the cardinality of each coset is the same as the cardinality of H. So I get, well, actually in the PowerPoint I use K, so I'll use K. So I get K is the number of right cosets. K times H, or the cardinality of H is then the cardinality of G. Hence, we have proven, because each of our cosets are the same size, each of them is disjoint, and the union of all of them is the whole thing. Therefore, any subgroup must divide, or the order of any subgroup must divide the order of the group, because we're going to get exactly the number of right cosets times the cardinality of the subgroup is equal to the cardinality of the group. And again, just because this K can be important, we just defined it as the index of H and G, and we gave that some notation so that we could talk about it. Do you guys have questions on that at all? Sure, so an example one. All right, let's look at, we're going to have a couple examples in here, so I'm going to go through this corollary and talk about it, and then I will have some examples after that, or along the way I will make some up. Is that all right? All right. Then what I want to say is if G is a finite group, then the cardinality, or the order of A rather, or the cardinality of the cyclic group generated by A will have to divide the cardinality of G. So let's actually look at something like that. Let's suppose I have a finite group. So let's look at Z2 cross Z8. Or Z4, let's say. What I want to know is, what is the cardinality of Z2 cross Z4? Or what is the order of that group? Well, because this is a direct product, which we did talk about last week as well, the direct product order is going to be the order of this times the order of this. Z2 has 2 elements in it. Z4 has 4 elements in it. So I'm going to get the order of this is 2 times 4. So we're going to have 8 elements. What are those elements going to look like? Well, I could list out all 8 elements if I wanted to. And I would get something that looks like 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3. I'm not going to write them all, but I wanted to at least give a representation of what these are going to look like, or order pairs, where these first elements are in Z2, and the second entries are in Z4. So you could get something like 1, 3 as well in there. Any questions on that one at all? So, just to point out, if we use Lagrange's theorem, the cardinality of this group is 8. So if we find a subgroup of this group, what are the possibilities for the orders of subgroups? Well, if I find any subgroups of this, the only possibilities are that the subgroup H has cardinality Well, what are the divisors of 8? Are 1, 2, 4, and 8. So if I find a subgroup, it's either going to have 1 element, 2 elements, 4 elements, or 8 elements. That is, we can't have 3, 5, 6, or 7 elements in any subgroup. All right. Now, taking that a step further, I said that, well, if I find a group generated by any one of these elements, so let's find the group generated by 1, 0, what's going to happen is that I'm going to get a subgroup of this group because this is the group generated by this element. Therefore, if I'm going to find this, this has to have either cardinality 1, 2, 4, or 8. And what we know is that any cyclic group is just going to be the multiples of this. So this is going to be the set of all n times 1, 0, such that n is in Z. But I can't have an infinite number here because this is going to have some type of repetition. So if I actually find these, 1 times 1, 0 is 1, 0. 2 is 0, 0. Negative 1 is negative 1, 0, which is actually 1, 0. And so really what I get are just the 2 elements, 0, 0, 1, 0. So the group generated by 1, 0 is 0, 0, 1, 0. And notice that the cardinality is 2. Therefore, the order of 1, 0 is going to be 2, because the order of the group generated by 1, 0 is 2. And again, 2 divides 4. Since the order is 2, we would say then the index is 4, because 8 divided by 2 is 4. Therefore, we have an order 2 and an index 4. And that would be an example using this is that, okay, if I find these subgroups, these are the only possibilities. All right. Go ahead. Sure. So I should write here, or 8. So if I pick any subgroup of this group G, then my only possibilities are 1, 2, 4, or 8. In this case, the cardinality, or the order of this group is 2. So what I'm claiming is my possibilities, the only possibilities are 1, 2, 4, 8, because those are the only divisors of 8. In this case, I get 2, so it does fall into my examples. So another way does that make sense? So if I'm trying to find any of my subgroups, I could never find a subgroup with 5 or 6 or 7, but I could potentially find one with 1, 2, 4, or 8. It's not necessarily guaranteed you get all of those, but in general, those are the only ones that are allowed. All right. So if we look at these all follow from that is that what I tried to illustrate in that example was that if I find the group generated by a single element, it will have to divide the order of G. In this last case we saw the order was 2, which divided 8, so that worked out. Also, if G is a finite group and A is in G, then what I claim is that A to the cardinality of G is equal to the identity element. All right, let's think about why that would be true. And let's look at this example. If I pick any arbitrary element in here, let's say 1, 3. Now, in the PowerPoint, I'm using product notation. Here I'm going to use addition notation. But what I claim is that this times 8 is equal to 0, 0. In fact, if I pick any element in here and I multiply by 8, I get 0, 0. Well, for this one case, if I take 1 times 8, I get 8, but I'm using mod 2. 8 mod 2 is 0. 3 times 8 is 24. 24 mod 4 is 0. So in this case, I do indeed get that 1, 3 times 8 is 0, 0. So it works out for that example. Now, what I claimed is more general. It's always going to be the case. And so why is that always going to be the case? Is let's suppose I have a group G and I have some A and G. What I just claimed was that the order of A divides the order of G. So let's say that the order of A is equal to K, then K is going to divide the order of G. Well, remember that when we talked about the cyclic group, what this means is that A to the K, so using multiplication notation, would be A to the K. If the order of A is equal to K, then A to the K is the smallest element, which A to the K is equal to the identity. So if we go back to when we were talking about generators and cyclic groups, if we find the group generated by a single element, if this was finite, then the cardinality is the smallest element K such that A to the K is equal to the identity. All right, so A to the cardinality of G is equal to A to the K times, let's say, N for some N, because I know that the order of this divides the order of this, because that was part 1 of my theorem, and because the group generated by A is a subgroup of the group G. Therefore, by Lagrange's theorem, this has to divide this. Therefore, the cardinality or the order of G is equal to K, which is the order of A, times some integer N, which means that this is A to the K to the N, but A to the K is the identity, and so the identity to any power is the identity. So if we take any element of G, some finite group G rather, and we take A to the cardinality of G, we are always going to get out the identity. So if we're working with finite groups, we can always say that A to the power of G will indeed just be the identity element. Does that make sense to everybody? All right. Now, let's assume, I'm going to skip that third one because we didn't quite talk about that in that section. But I'm going to move on to the fourth point here, is assume that P is prime. And if P does not divide A, then A to the P minus 1 is congruent to 1 mod P. And in general, A to the P is congruent to A mod P. All right. So let's do that one. So now let's say I have a group of cardinality P. Where P is a prime. Then, oh, actually, I'm sorry. What I have here is I'm just working with a set of integers. So I have Z, and I'm going to let A be an element of Z. And so if A is any integer, I want to show that A to the P is congruent to A mod P. Are you guys following what we're trying to do at least so far? So now we want to show this in general, but if P does not divide A, then we want to show in particular that A to the P minus 1 is equal to the identity element, which on Z would, to the identity element. So on Z, the identity element is 0. Oh, so the identity element is 1 under multiplication. So I'm going to show A to the P minus 1 is equal to 1 mod P. There we go. Now, if P divides A, notice this isn't true, because 0 to the P minus 1 is 0. 0 is not congruent to 1 mod P, because if anything's divisible by P, then it's congruent to 0 mod P, so this one wouldn't be true. But 0 to the P is congruent to 0 mod P. So I'm going to start with this one and just show in general, for any integer, A to the P is congruent to A mod P. All right, let's kind of think about the context of what's going on here, though, is that what's really happening here is if I'm looking at things of the form A to the K for an integer K, and I want to know what happens mod P, what I can really do is look at Z sub P. So I'm going to do a roundabout talk here, and I'm going to say, what does Z sub P look like? Or what do the integers mod P look like? All right, so if we think about the integers mod P, what is the cardinality equal to? So the cardinality of Z to sub P is just P. Because remember, Z sub P is just the set consisting of 0, 1, 2, 3, P minus 1. Is that okay with you? Does that make sense? All right. Now, so if I have Z sub P, the cardinality is P. Therefore, if I look at it with respect to addition, this is a group, and then therefore P times any of these elements is going to be 0. So if I multiply any of these things by P, I know I'm going to get out 0. What I want to look at next is, if I include 0, notice that this as under multiplication, so let's take Z sub P under multiplication instead of addition. If I include 0, then I don't get a group because the identity is going to be 1, and there's no inverse for 0 because 0 times anything is 0. Is that okay with everybody? So I'm going to take Z sub P not 0 under multiplication, and I'm going to talk about what does that look like. In particular, I want to know, is that a group? So for it to be a group, I just need an identity. I need to be associative. I need to have, I need to be closed under, so closed. I need to be associative. I need to have an identity. And I need to have inverses. So to show that this is a group, I have to show that those things are true. Is that okay with everybody so far? All right, let's think about this. To be closed, what I have to show is that if I take the integers mod p and I take a times b, it has to be back in z sub p. So now I'm taking a times b mod p, so I'm going to get this as a times b mod p. So what I know is that for any a and b in z sub p, a times b is again in z sub p. But if I wanted to start with non-zero, what I have to show is that for a and b non-zero, that I'm going to end up back in z sub p. So what I really have to show is that if I take a and b are non-zero, this cannot be congruent to 0 mod p. So for closure, I have to show that if I take two non-zero integers, or two integers that are not divisible by p, so non-zero integers in z sub p, I multiply them together, I again won't get 0. Is that okay? All right. So I'm going to do this one by contradiction. Let's suppose a times b was equal to 0 mod p. What does it mean to be congruent to 0 mod p? Is that p divides a times b, right? You guys following that one? Okay. So in order to be congruent to 0 mod p, that means that p divides a times b. But what we proved is that this is, if p is prime, and p divides a times b, that means p divides a or p divides b. So we showed that by definition prime was something where if it divides a times b, it divides a or it divides b. But we were saying what? So that's exactly right. I'm going to be a little bit more specific, but if p divides a, then a is congruent to 0 mod p. And if p divides b, b is congruent to 0 mod p. But I claim that neither of these was congruent to 0 mod p because we're in z sub p not in 0. So therefore a and b are non-zero, so I can't multiply them together to get a 0 out. Therefore this set is closed under products. Does that make sense? So if I'm working in z sub p and I multiply two numbers and get out 0, I had to have one of those numbers was 0 to begin with. So if I work with the non-zero numbers, they will be closed under multiplication. Is my multiplication going to be associative? Well, yes, I do know that one. We have actually proved that before when we're talking about z sub p, the multiplication is associative. So if I remove 0, since I'm closed, I'll still be associative. So I'm not going to walk through that proof again, but we will be associative. Well, do I have an identity? What is the identity for multiplication? I think that's just 1. So I'll get to inverses next, but for identity, it's just 1, right? Because 1 times anything is the anything. So that's still going to act like an inverse in z sub p. So we still have an identity. What we have next is, I need to show inverses though. So what has to happen is if a is in z sub p not 0, I have to find a b such that a times b is equal to the identity 1. So now, if I was doing z sub 3, I'd have 0, 1, 2. Well, 1 times 1 is 1. 2 times 2 is 1. So each of those have an inverse. In 5, I could actually go through and say 1 is its own inverse. 2 times 3 is 1. And then 4 times 4 is 1. So we have inverses for each of those. But if we're working with z sub p in general, we have to think about this another way. So what I'm going to do is I'm actually going to say, if I have an arbitrary a in z sub p not 0, what is the greatest common divisor of a and p? Well, help me out here, guys. It's Very good. So that's where I'm going. But I want to start off with just what is this as an actual number? Is what are the divisors of P? Just 1 and P, right? Because it's prime. So 1 and P because P is prime. So if A is in Z sub P non-zero, can A be equal to P? No, because it's either 0, 1, 2, 3, 4 up to P, and it can't be 0. So A is not divisible by P. So what is the greatest common divisor of A and P is? Well, it's not P, so it has to be 1, doesn't it? All right, and then T, you were saying that it's also equal to AK plus PL, right? By the Chinese remainder theorem. All right, very good. So what that means is I know the greatest common divisor is 1. Therefore, AK plus PL is equal to 1 for some integers K and L. But if I look at this mod P, what is this equal to mod P? What's P times anything mod P is 0 times anything. So this is just 0, isn't it? So mod P anyway, A times K is congruent to AK plus PL mod P is congruent to the greatest common divisor of A and P is equal to 1 mod P. So therefore, we get that by this theorem, for any A in Z sub P non-zero, there exists an integer such that A times K is congruent to 1 mod P. Therefore, every element in here will have an inverse because there will exist a K such that A times K is equal to 1 mod P, and this K becomes my inverse. All right. Z sub P not 0 under multiplication is therefore a group. What is the cardinality of this group? How many elements do I have in here? Well, I would P minus 1. Very good. Very good, because I had P. I removed 0, so I have P minus 1. Now, that's a group with P minus 1. So if I take anything in here, say A, what do I know about A to the cardinality of the group G, which would be in this case A to the P minus 1, is equal to what? Well, in step 2, we proved that if I take any element of a group and raise it to the power of the group, I get the identity on the group. So this is congruent to 1 mod P. Right? So therefore, A to the P minus 1 is congruent to 1 mod P for all integers that are not divisible by A, because all integers that are not divisible by A are congruent to something non-zero mod P. So therefore, A to the P minus 1 is congruent to 1 mod P. And notice we did absolutely no arithmetic in that one. I mean, other than counting the number of elements here. But we didn't have to actually do anything. We just know from Lagrange's theorem that this has to be true, which is actually pretty amazing. I think that's just a really cool proof, because you think I'm going to like do some factoring or something here, and I do none of that. I just say, hey, this is a group. It has cardinality P minus 1. So the order of A has to divide the order of the group. So A to the order of the group has to be the identity, and so we get out our desired result. The only other option was if we throw 0 in, we know that 0 to the P is congruent to 0 mod P. And if we use this one and we multiply both sides by A, we get A to the 1 times A to the P minus 1 is A to the P is congruent to A mod P. So we don't quite get A to the P minus 1 is equal to 1 for 0. But if we want to include 0, we can always get that A to the P is congruent to A mod P by either multiplying both sides here by A, or just noticing that 0 to the P is congruent to 0 mod P. Makes sense. All right. What is x plus y to the p congruent to mod p? Well, according to my theorem, I just said x to the p was just equal to a, or a to the p was congruent to a, so x plus y is congruent to x plus y mod p. What's x plus to the p is congruent to x mod p, and y to the p is congruent to y mod p. So if I combine this together, x plus y to the p is congruent to x to the p plus y to the p mod p. Why in the world did I take the time to even do that is because this is a really cool example. If you guys are ended up teaching and you ever have people working in, pre-calculus or before regular algebra, you're going to see someone take some type of power and they distribute it because obviously x plus y squared is x squared plus y squared, or the square root of x plus y is the square root of x plus the square root of y. And you just have to keep yelling at them to say, no, you can't distribute powers. You can't distribute powers. And then when you get far enough, hey, you can distribute powers if you're working with p and mod p, where p is prime. So I think I've heard this called the freshman's delight. You can actually distribute powers. How cool is that? That's just awesome. You guys aren't talking, so I'm assuming that you turn your headsets off and you're screaming with joy at how awesome that is. All right. So there you go. There is a pretty neat result following just from Lagrange's theorem, and so I did want to talk about that. The next thing I did want to talk about is that if I have a group of prime orders, such as z sub p, can I find all subgroups of z sub p? So let's actually go to the chalkboard and talk more about z sub p. And I want to find all subgroups. I know that the cardinality of z sub p is equal to p, so if I have a subgroup H, what can the cardinality of H be for any subgroup of z sub p? It's either 1 or p. So H either has order 1 or p, because those are the only divisors. If the cardinality of H is p, what is H equal to? Well, H is just the whole thing, isn't it? Because H is a subset of z sub p, but it has all the elements of z sub p, so it has to be z sub p. If H is equal to 1, what does H look like? Well, it's just a trivial group consisting of the identity element. That's the only group with order 1. You have one element, it has to be the identity, has to be in there, so that's the only possibility for H. So what are the only two subgroups of z sub p for any prime p are either the whole group or the trivial group consisting of the identity. And we have therefore classified all subgroups of any group, and we can do this with any group of prime order, as we can just substitute this for G, the whole thing, or just the trivial groups consisting of the identity element. That's actually pretty neat too, because I just have a group, it's prime order. I want to find all subgroups. That sounds like a very complicated problem, but, well, the order has to divide the order of the group, so I really don't have that many options. And I get out, there are exactly two subgroups of that prime ordered group. All right. Also, each group of prime order is cyclic, and it's generated by any of its non-identity elements. So why is that going to be the case? Well, if we follow through, we get that for any element a to the p, we can multiply a to the p, a times a times a, and we're going to get, following our previous one, that a to the p minus 1 is congruent to the identity mod p if it's non-zero for multiplication. And we get that it's going to end up looking just like, well, let me write this up at the board. So let's just suppose that the order of the group G is P. If I have the identity element E, then E to the anything is just E, and E to the P is E. Let's say A is not equal to the identity. Then what I get is that the order of A has to divide P, but the order of A cannot be 1 because A to the 1 is not the identity, so the order of A has to be P. Therefore, the group generated by A has cardinality P, so the group generated by A is a subgroup of G, so the group generated by A has to be G. So if I start with the identity, the group generated by the identity is just the identity group, or the group consisting of the identity. But if I pick something that's not the identity, the order of A cannot be 1 because A to the 1 is not the identity. Therefore, the order has to be P. Therefore, the size of the group generated by A has to be P, which is the same as the size of the group. So G just has to be generated by any of its non-identity elements, which actually means that every group G that looks like P is going to end up looking like Z sub P, because I could pick any one of the elements and call that my 1. It's going to generate the whole thing, and then I'm going to have a 0 in there. So each of these will end up looking like this. Any questions on that? All right. So I just want to point out, this was a nice quick theorem, wasn't it? It's, if H is a subgroup of a finite group G, then the order of H is a divisor of G. And it seems like such a simple thing, but from that we get all of these things follow immediately from that, which is pretty amazing. And so this is really just a great theorem that really gives us a lot of nice number theory results about groups, and it just helps us find subgroups a lot faster. All right. So what I want to do is, I think instead of working with the symmetries of a square, I'm going to work with Z2 cross Z4 because we were working on that one earlier. So I'm going to stick with that example. But what I want to do is find all of the subgroups, and I want to display those in a subgroup lattice. So what does that even mean? Well, we'll talk about that. So if I look at Z2 cross Z4, I'm actually going to make a Cayley table really quick. I had 0, 0, 0, 1, 0, 2, 0, 3. Oh, I have to be much smaller than that. 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, 0, 0, 0, 1, 0, 2, 0, 3. All right. So to make a Cayley table, I'm going to get the same things out here, 0, 0, and I can write these all out. If I add 0, 1, I'm going to get 0, 1. Well, I'll just write these down. 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, 0, 2, 0, 3, 0, 4, which is 0, 1, 1, 1, 2, 1, 3, 1, 0, 0, 2, 0, 0, 0, 1, 0, 2. Sorry, this should be 0, 3, 0, 0, 0, 1. All right. I'm already getting tired of writing these out. There's going to be 64 of them. I don't really want to do it, but if we write out the whole Cayley table, it does make it easier to find the subgroups. But I just want to go through and try to find those with you guys. And so I'm going to start off, and I'm going to find all of the subgroups. So what is the subgroup generated by 0, 0? So if I have 0, 0, that's the identity. And so I get the group which is generated by the identity. It's just the identity. So one subgroup will be the group consisting of 0, 0. All right. If I find the group generated by 0, 1, I'm going to make you guys think about that. What's the group generated by 0, 1? Well, we get 0, 1, 0, 2, 0, 3, 0, 0. And then if I take this set and add it to this set, notice that each time I add, the first component is going to be 0, and the second component is one of those. So I'll have another group is 0, 0, 0, 1, 0, 2, 0, 3. How about the group generated by 0, 2? Well, if I add that together, I get 0, 0. So actually, this set, 0, 0, 0, 2, is closed. So I would get 0, 0, 0, 2 would be another group. Following me so far? What is the group generated by 0, 3? I think that's 0, 0, 0, 1, 0, 2, and 0, 3 again, right? Which we have up here already. How about the group generated by 1, 0? Well, I'd have the group generated by 1, 0 is 1, 0 plus 1, 0 is 0, 0. And so actually I'd be closed there. So that's another group. Notice the group order of the entire group is 8. So far I had 1 element, 4 elements, 2 elements, 2 elements. So 0, or 1, 2, 4, or 8 were my options. So I'm still falling within those. What's the group generated by 1, 1? Well, 1, 1 plus 1, 1 is 0, 2. So I would say 1, 1 plus 1, 1 is 0, 2. Plus 1, 1 again is 1, 3. So 0, 2 plus 1, 1 is 1, 3. And then if I add 1, 1 again, I get 0, 0. So 1, 3 plus 1, 1 is 0, 0. And then I have to add those together. So 0, 2 plus 1, 3 I think is going to be 1, 1. So now if I add those in, I should also get 1, 1 plus 1, 1 is 0, 2. That makes sense. 0, 2 plus 1, 1 is 1, 3. And so if I have those, I have 0, 0, 0, 2, 1, 1, 1, 3. And so I'm going to have 4 elements in that group, is those 4 elements. One, 3, 1, 1, 0, 2, and 0, 0. All right. What is the group generated by 1, 2? Well, I'm going to get 1, 2 plus 1, 2 is 0, 0. So I'm going to get a group consisting of just 1, 2, and 0, 0. What's the group generated by 1, 3? Well, if I do 1, 3, I'm going to actually just end up getting the same thing as 1, 1. So I'm going to get exactly the same group. I know this is taking a while, but now I have to do 2 at a time. What I wanted to point out is when I picked 0, 1, I had a 4-element subgroup, right? So if I pick 0, 1 with any one of these elements in it, what do I have to get? So if I take 0, 1 and generate with 1, 1, then I can combine both of those, right? So just using 0, 1, I get 4 elements. So if I throw this one extra element in, that means I have at least 5 elements in my group. So if I have at least 5 elements in a subgroup of an 8-element group, how many elements do I have to have in my subgroup? So I have at least 5. It has to be 1, 2, 4, or 8. Therefore, it has to be 8, right? So if I take this and I add anything else in, I'm going to get the whole thing. So I don't really have to check this with any one of these other ones because I get the whole thing. The same way when I generate it with this, I get this whole thing. So I had 4 things in there. So if I throw any of the other ones in, I'm going to have at least 5. So I'm going to generate the whole thing. So I'm going to erase this for some room. And so if I do that, what I end up with is I have this group, this group, this group, this group, and this subgroup, and then I have basically the whole thing, which was Z2 cross Z4. And I have to think about, are there any more? Well, these 4-element ones, I can't throw anything else in. So I might try these 2-element ones, and I'll try to throw something in. So if I take this group, and I throw in this one, I'm going to end up with the whole thing, because I'm going to have at least 5, because I already had there. So the only thing I would think about is, what if I had 0, 0, 0, 2, and 1, 0? Could I make a new group? Because here I'm combining 2-element groups. So the union there is these. But if I want to close that, I would also have to get 1, 2, which is actually, yeah, that's right. So now if I look at that, notice that this one is now closed, so that is another group. So notice that out of all of these, this is actually the only subgroup which is not cyclic. Besides the entire thing. The entire thing is not cyclic because it's not generated by one element, because I found the subgroups generated by each one element, and none of them were this, so this is not cyclic. This is also not cyclic, but all these other ones are. So now I have 4 elements, 4 elements. I've combined my 2's and 2's together the best I can. Are there any other options? Well, since I have 4, if I throw any more in there, I'm going to get the whole thing. So actually, using Lagrange's theorem, I know these can be the only subgroups because I have to have 1, 2, 4, or 8 elements. And if I try to combine things any other way, I'm going to end up with at least 5, so I get the whole thing. Does that make sense? Go ahead, Kelly. What's your question? So, just as a point, the order of Z4, this is a cyclic group, but the order is not prime, because this is generated by 1, because if you start with 1, you get 2, 3, and then you end up with 0. So you can have a non-prime order group which is cyclic. However, what you can't have is a prime order group which is not cyclic. So if it is prime, it has to be cyclic, but you can still have a cyclic group which is not prime order, such as this one. This one has order 8, so that means at least potentially it could be not cyclic. And in this case, it ends up being not cyclic because we're taking a direct product and it just doesn't work out. And the reason why I know that is I tried each of the elements. I went through all 8 elements and found the group generated by those elements. And I never got out the whole thing starting with 1 element. I had to start with at least 2 to get the whole thing. So we would say that this is not cyclic because none of the 1 elements gave me the whole thing. Does that clear that up? You're welcome. All right. So now I'm just going to write out, and what I want to do is, what is a sublattice? Well, what a sublattice is that I'm just going to write these out so that if I go up, the smaller one's contained in the bigger one. So what I'm going to say here is I have the group generated by 0, 0, and I'm going to write these out using generators when I'm making my sublattice just because it's less to write. So this is the smallest subgroup of this, so I'm going to put this at the bottom. Now, for example, I would say something like the group generated by 0, 2 is right here. That contains 0, 0, and 0, 2. Therefore, it contains the group consisting of 0, 0. So by putting this above, that's saying that this group is a subgroup of this group because all these elements are contained in these elements. And each of those are groups. In the same way over here, I'm going to put the group generated by 1, 0 because 1, 0, 0, 0 contains the group 0, 0. So this is contained in here. Now, I want to point out we could also put, let's say, 0, 0, 0, 1, 0, 2, and 0, 3, which is the group generated by 0, 1. And now, technically, this contains this, so I want a line drawn down like that. However, because this also contains this one, instead of drawing my line like that, I'm going to need that one up here. I'll just have to remember it. And then I want a line drawn up here to the group generated by 0, 1. So this is saying that this is contained in this, but this is contained in this is also contained in this. So I'm fashioning it out so that if each one contains another one, I'm drawing a line down for the one that contains it. Now, if I kind of build myself up, these were the 2 element ones. Here's one 4 element one. Here's the other 4 element one is the one generated by 1, 1. And so if I look at the one generated by 1, 1, I get 1, 1, 1, 3, 0, 2, 0, 1. So actually, this one contains 0, 2, and 0, 0. So the group generated by 1, 1 is going to contain this group, but it does not contain this group or this group, so I'm only drawing a line down that direction. The other 4 element group was 0, 2, 1, 0, so the group generated by 2 elements. So now if I take the group generated by 0, 2, 1, 0, that's going to contain these 2, so I'm going to draw a line both directions. Notice, however, that it does not include this group or this group, so I'm not going to draw a line going down at all, and those are going to be considered, okay, so they're on their own level. And so I have 1 element groups, 2 element groups, 4 element groups. And so I said if they each contain each one below by drawing lines down. Now I have almost all of them. The only thing I have left is the entire thing. So I would have Z2 cross Z4. And notice that contains everything. So at the top here, I'm going to draw a line going down. And so that would be a sublattice of the subgroups. So what's happening here is then this contains everything. This one contains this one contains this one contains both of these. These 2 contain this one, and so we get all of that kind of working out in that manner. So we found all of them, and we just tried to ask which one is contained in which one. And I started with the identity one, and I built myself up. I started with 1 element, then 2, then 4, then 8. And so each time I'm writing down all those 1, 2, 4s, I'm saying, okay, this one contains these. So therefore, this is a subgroup of this, 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 and so I'm notating that pictorially. And so if I want to pictorially do that, that's how I would do that. And this is called I think I called it a sublattice on accident. It's just a lattice of the groups of subgroups. So the lattice of the groups of subgroups would pictorially look like that. Now, we haven't talked too much about it, but if we take the intersection of these two groups, we'll get this group. The intersection of these two groups is this group, and we notice that the intersection of any two groups is again a group. And so if we actually read off and go down to the point where they meet, then the intersection of those groups is going to be the smaller one where they meet. So the intersection of these two is again this one. Whereas the intersection of this one and this one we'll continue down to where they meet, so it's going to be that one. Now, with unions, you don't necessarily get a group, so you get the group generated by the union. So if I take the group generated by the union of these two, I'm going to get the smallest one containing both of them, so it's going to be that one. The group generated by these two ones is going to be the whole thing. And so again, you can kind of read from this chart then, what is the intersection of two subgroups? What is the group or the subgroup generated by the union of the two subgroups? And that's why we're calling it a lattice, because we have unions and meets and joins in there, or intersections and the group generated by the union. And so you get a nice pictorial representation of exactly what's going on and where you're going to end up depending on what elements you have in there. Is that okay with everybody? If not, if we just find the lattice of subgroups of Z4, let's say, we would have Z4, we'd have the group generated by 2, and we'd have the group generated by 0. And so the lattice of subgroups of Z4 would be these are the only 3 subgroups. Because you either have one element in it, 2 in it is 0 and 2 is the only way you can have 2, or you have all 4 in it. And so you could do something like this pictorially to say, well, there are all the subgroups of Z4, and there's how they're related. This is contained in this, is contained in this. And so it makes what you'd call a chain, because it is a chain. And so having kind of a picture to look at to see how the subgroup fits together is a nice thing to have to compare. Obviously, Z2 cross Z4 is much more complicated than Z4. There's a lot more subgroups, so our lattice became more complicated. Was that okay with everybody? All right, very good. All right. I'm going to actually just stop there. I was just trying to think about, I think there's enough done today that I feel like I filled your minds with amazing, interesting stuff. So next Monday we'll pick up and talk some more about cyclic groups, and then we'll move on to the next section. But I just want to point out, okay, there you go. So there will be homework due next Monday. I will post that pretty soon here, as soon as I get around to it, so within an hour or so. And it'll be just from chapter 17 because the stuff we did on Monday was just a review of homework. So there will be some homework from chapter 17. All right, any other questions before I let you guys go? You have a nice day as well.